Hello there. Let's take a look at chapter 4, the covalency chapter that we'll be going over for the next 2 weeks, and see what we can do to get started. As we always do, we'll take a look at some of the ideas in chemistry which relate to medicine with a couple of scenarios to whet our appetite. And so for the first one, doctor asks you to fetch a bottle of nitrous oxide from the cabinet. You go to the cabinet and you see bottles marked as NO, NO2, N2O, and N2O5. Which one is nitrous oxide? We'll talk about that during the chapter. Later on, you're asked to fetch a bottle of formaldehyde. Looking at the Lewis structures which are drawn in the bottle, which one would be formaldehyde? And what is it about it that we can recognize? Finally, when asked why the active form of aspirin is not orally given to the patient, you reply to the patient that it's too caustic. However, you're not sure how to explain what you mean by caustic. We'll talk about the caustic nature of aspirin and talk about what it is in the molecule specifically that makes it caustic and how that can be masked. So let's move on with chapter 4. So we had talked about ion chemistry in the previous chapter, which was this idea of atoms coming together as they do in covalent chemistry by overlapping their shells that contain electrons, and therefore the atoms would fight over those electrons in the mutual space. Now we had said that the non-metals and ionic compounds had the advantage because they had fewer shells and were able to more closely or strongly attract electrons because the electrons were closer to the atom's nucleus, or it just had more protons to generate more attraction. Either way, there was a shift of electrons from the metal to the non-metal. The metals became positively charged and the non-metals were negatively charged. It was that electrostatic attraction that held the ions together. However, with covalency, we're just looking at metalloids and non-metals, all of the elements tucked in the top right-hand corner of the table, where we find the elements with the best and highest electronegativity. So these elements are all good at attracting electrons, and when they come together to form a bond, it's a tie. That attraction for electrons is so closely matched that the atoms cannot get the upper hand. So by default, the atoms share the electrons to make covalent bonds, sharing pairs of electrons between the two atoms. However, just like Goldilocks' porridge, it's got to be just right. And that optimum bond length from one nucleus to the other comes when we get the lowest possible energy for the bond. You can see it here on our graph in the middle. Optimum energy, so optimum bond length, and that's the length of bond we see for these two atoms. However, if the atoms get too close to each other, we see that energy of that bond start to rise, and the bond becomes more unstable. That's because as the atoms get closer to each other, positively charged protons in one nucleus become aware of positively charged protons in the other nucleus. Proton to proton repulsion, and that raises the energy of the bond. On the other hand, if the atoms get too far apart, we lose that attraction between the negatively charged electrons which are being shared and the positively charged protons in the nuclei. So if the bond gets too long, the energy rises too high, the bond breaks and the atoms just drift apart. Remember, the strength of that bond is the shared electrons, those negatively charged pairs of electrons, feeling an attraction to the protons in each nucleus. However, just as we saw in ion chemistry, it's still the same end result which is desired. We want the shell to be completed. We want the elements to have a configuration like the noble gases in the last column, the last group of the periodic table. So these atoms are sharing pairs of electrons to make these covalent bonds, and the target is to share enough electrons, make enough chemical bonds to complete the shells, to complete the octets, just as we did in ion chemistry, except are sharing instead of stealing electrons from each other. So we can draw Lewis structures to show how many electrons are in the atom's outer shell, and therefore show how many electrons the element needs. Sodium, that's the first element in the third row of the table, 1 electron in its third shell. Aluminium, the third element in the third row, with 3 electrons, but if it's going to complete its octet, it would need another 5. Phosphorus, with 5 electrons, needing an octet, needing to look like argon, would need 3 more to complete its shell. Sulfur, with 6 electrons, would need 2 more. Chlorine, with 7 electrons, would need 1 more. Now, the decision to pair the electrons up or leave them as individual dots is just a reflection of how they fill the subshells following Hund's rule. So for aluminium, those first 2 electrons go together to fill the S subshell, and leaving 1 for the P unpaired. With the phosphorus, first 2 electrons paired up to fill the S subshell, and then the 3 remaining, following Hund's rule, go into separate orbitals in the P subshell before even thinking about pairing up. Sulfur, with 2 in the S, paired up, and then the 4 in the P. The first 3 go into separate orbitals, then that last and 4th electron pairs up with one of the electrons in the first orbital. So we're really just following Hund's rule when we show the electrons, the Lewis structures, with paired dots or unpaired electrons. Similarly for ones down below in the second row, which we can quickly fill in. So for carbon of course is the 4th element in the second row. So 2 electrons initially going in to fill the 2s subshell, and then 2 electrons unpaired in that p subshell with 3 orbitals. Oxygen with 2 electrons in the 2s, then 2, 3 electrons initially in the p subshell, then a 4th, like sulfur, pairing up, leaving it with 2 unpaired electrons. Nitrogen, 2 dots, 2 electrons going into the S, then initially 2, 3 electrons going into those separate orbitals in the p subshell, giving it 3 unpaired electrons. And finally, fluorine, element 7, 2 electrons paired in the S, then initially 1, 2, 3 in the P, and then a 4th and a 5th electron, room for just 1 more, so 1 unpaired electron. So drawing those Lewis dot structures using a count of boxes in the appropriate row of the table not only tells us how many electrons the element has, but it also tells us about how many electrons the element needs to fill its shell. Carbon has 4 electrons but needs another 4, hence we expect 4 chemical bonds to be formed. For every electron it needs, it normally implies a chemical bond. Likewise with oxygen, which needs another 1, 2, we would normally expect 2 chemical bonds. Nitrogen with 5 electrons needing 3 more, we would expect 3 chemical bonds. And fluorine, like other halogens needing 1 more, we would expect 1 chemical bond. So in chapter 3, we used a group to represent the electrical charge we would expect. Now we can use the groups to represent the number of chemical bonds we expect. For every electron needed, that implies a chemical bond has to be formed. The atom uses one of its own electrons and borrows an electron from the other atom that it's making the chemical bond with. Oh, tidy up my pictures before moving on. So let's look at a couple of examples. We talked about elements like hydrogen, oxygen and nitrogen as being diatomic elements back in chapter 1 and 2. And now, as we use these electron dots, we can show why they are diatomic, because it allows the elements to complete their shell by bonding with one other atom of that element. So of course hydrogen, that's the first element in the table. We can show that just in case people have forgotten. First element in the table, first box in the first period, so just one electron in its outer shell, and it wants one more so that it can look like helium. So we take a second hydrogen atom with a second electron, and they share those two electrons to make a chemical bond in that mutual space. Normally we represent the bonds as lines rather than the dots, and that gives us a completed shell for both atoms. They're sharing that pair of electrons so that the outer shell of each looks like helium. So a diatomic hydrogen gas. Next one with oxygen. Oxygen, as we look at it in the table again, element number 1, 2, 3, 4, 5, 6 in the second row, 6 electrons in its shell. It needs 1, 2 more electrons to complete its shell, and that implies 2 chemical bonds. So if we bring in another oxygen atom and encourage it to share 2 of its electrons, so 2 from the first atom, 2 from the second, those 4 electrons go together to make a double bond in that shared space. And we complete the octet of each atom. Each oxygen sees 2, 4, 6, 8 electrons. Same with the oxygen on the right, 2, 4, 6, 8 electrons. Octet complete. We draw the bonding electrons as lines, each line being 2 electrons, so we can differentiate between the bonding electrons shared between the atoms and the lone pair electrons which belong to a specific oxygen atom in the molecule. So diatomic oxygen gas 2. Finally, nitrogen. Again, looking at the periodic table for nitrogen. It's the 5th element in the second row, and it needs 1, 2, 3 more electrons to complete its shell. That normally implies 3 chemical bonds that need to be formed. And sure enough, using 3 of its own electrons and borrowing 3 electrons from the neighbor, we get 1, 2, 3 pairs of electrons, 3 chemical bonds, what we normally call a triple bond between the 2 nitrogen atoms. They complete their shells, and so we get diatomic nitrogen gas. We can actually follow some simple rules to make a Lewis structure of any molecule, just about, although we'll focus on the relatively simple ones with just one atom at the center of the molecule. As we said, electrons used for chemical bonds will draw as lines, each line being a pair of electrons. And electrons not used in chemical bonding will leave as dots, and we'll usually pair them as lone pairs. The position of the element in the table gives us a lot of information, like carbon. It's got 4 valence electrons, 4 electrons in its outer shell, because it's the 4th element in that row. And it needs to make an octet, like neon. It needs another 4, so we expect 4 chemical bonds. Sulfur In the third row is the sixth element, so it has 6 valence electrons. It needs 2 more to make 8, so we expect 2 chemical bonds. So for drawing Lewis structures, and let's take an example like hydrogen cyanide, we count the valence electrons first of all. That's 1 for hydrogen, 4 for carbon, and 5 for the nitrogen. That gives us a total of 10. We're going to use exactly 10 electrons to make this molecule. That should always be an even number for the electron count because the electrons are filling the orbitals and subshells with even numbers of electrons. Now, choosing the central atom, normally we would go by the electronegativities in the non-hydrogen atom with the lowest electronegativity, but we don't always have a table of electronegativities on us. So, as a simple guideline, for the central atom, you would choose the element which needs the most electrons. The more electrons it needs to fill its shell, the more chemical bonds it's going to form. And that's, of course, counting the boxes past the element. Like for carbon, another 1, 2, 3, 4. Phosphorus, another 1, 2, 3. Selenium, another 1, 2. And iodine, another 1 box, another 1 electron. So the element needing the most electrons makes the most chemical bonds. That's what we sometimes call the combining power. Just a fancy term for the number of expected bonds. So carbon would win over phosphorus because carbon needs 4 electrons and would be expected to make 4 bonds, while phosphorus only needs 3 electrons and would normally be expected to make 3 chemical bonds. Now the elements sometimes break these rules, but it's a good basic guideline to get us started. Similarly, nitrogen needs 3 electrons and therefore makes 3 chemical bonds normally, while sulfur normally makes 2 chemical bonds. So nitrogen is more likely to be the central atom over sulfur, or oxygen, which needs 2 electrons and would make 2 chemical bonds, is more likely to be the central atom than hydrogen, which only needs 1 electron and therefore normally only makes 1 chemical bond. However, sometimes there's a tie because we're dealing with elements which are in the same group of the periodic table, like nitrogen and phosphorus, or oxygen, sulfur, and selenium. So when we have a tie for the element which is going to make the most bonds, we then look at these elements and look for the element which is physically bigger. Bigger atoms also make more chemical bonds. So phosphorus would win over nitrogen because phosphorus is below nitrogen in the table. So phosphorus wins. Comparing sulfur to oxygen, sulfur is below oxygen in the table, so it expects sulfur to make more chemical bonds. So first and foremost, go with the element which is more greedy for electrons, and if there's a tie, then look for the element which is physically bigger. We will talk about examples where that choice of central atom sometimes follows a different rule because of hypervalency, but more about that later. So we've counted our electrons, we said 10. We've chosen our central atom, that should be carbon, because it needs to make 4 bonds, while a nitrogen only needs to make 3, and a hydrogen only needs to make 1 bond to complete its shell. So with our central atom carbon, we connect it to the other atoms in the molecule, hydrogen and nitrogen, and we get a basic skeleton for the eventual molecule. Skeleton framework is not going to change. Now that used 2 electrons each time for each of those bonds, to carbon to hydrogen or carbon to nitrogen. That leaves us with 6 electrons, and the remaining electrons are used to fill the shells of the outer atoms first. The hydrogen sees the lone pair, so it has its duet for its bond to look like helium, but nitrogen, of course, needs an octet. So we use those remaining 6 electrons, 2, 4, 6 lone pair electrons, together with the bonding pair, and so nitrogen sees an octet of 8 around it. Always start adding the extra electrons, those electrons which will be drawn as lone pairs, add them to the outer atoms first. Never put electrons on the central atom unless there's nowhere else for them to go. Now we have run out of electrons, of course, when we complete the octet of the nitrogen, but the carbon in the middle still doesn't have an octet. So this is where we invoke our fifth and final rule for emergencies. If we run out of electrons and we still have octets incomplete, then we borrow the electrons we've put in and turn lone pairs into bonding pairs. So sharing 2, 4, 6 electrons with the carbon, we get an octet for both carbon and the nitrogen, and of course a duet for hydrogen. And that's when we know we're finished. If the shells are complete, if the shells are filled, then we've got chemical bonding that gives stable molecules. Let's take a look at some extra examples. You can pause the video at this point and try these for yourself, and then we'll go over the answers once you unpause the video. Okay, let's take a look at these. And remember, we'll follow the 5 steps we've outlined in the first part of the lecture. Let's use black this time. So starting off with the chlorine gas, of course the halogens in group 7, another example of diatomic molecules, and we can show why with covalency. So Cl2, we look at the position of chlorine in the periodic table. It's the 7th element in the row. It's got 7 electrons in its outer shell, and it's looking for one more to complete its octet like argon. So as we look at our example here, that's 7 electrons for the chlorine and 7 electrons for its neighbour. So that's going to be a total of 14 to make our Lewis structure. We put the 2 chlorine atoms at the centre of the molecule. That's of course used a pair of electrons right away. Keep count of how many electrons you've got left as you're doing this. We'll use the remaining electrons to complete octets, just randomly starting with one of the atoms, so down to 6, and the other 6 is another 3 lone pairs, and octets are complete. The chlorine on the right, it sees a total of 8 electrons around it, 2, 4, 6, 8. The chlorine on the left sees a total of 8 electrons, 2, 4, 6, 8. So sharing that pair of electrons in the middle gives a completed octet for each chlorine atom, using one of its own and borrowing the electrons from the neighbour, which we had talked about. Once shells are complete, you've normally finished the Lewis structure. Our only exception to that is going to be hypervalency, but more about that later. Second one, water. Again, looking at the electron count, hydrogen and oxygen. And a periodic table tells us it's 1 electron for a hydrogen and 1, 2, 3, 4, 5, 6 electrons for an oxygen. So 1 times 2, then 6 for oxygen, gives us a total of 8. Choosing the central atom, oxygen needs more electrons to complete its shell. If it's going to look like neon, it needs 2 more, or hydrogen only needs 1 more to look like helium. We expect oxygen to make more chemical bonds. So the oxygen goes at the center. We connect it to the hydrogens using a pair of electrons each time. So we're down to 4. We use the remaining electrons to complete octets because the hydrogens have their duets. So now we do put the electrons on the central atom this time. There's 4 electrons, there's 2 lone pairs. We've used up our electrons and octets are complete. Duets for the hydrogen and an octet for the oxygen in the middle. 2, 4, 6, 8. Next one, going to ammonia, NH3, a basic compound. Again, using the periodic table. 5 electrons for nitrogen. 1, 2, 3, 4, 5 boxes to reach nitrogen, 5 electrons. Of course, each hydrogen needing just 1 more. So electron count is going to be 8 this time. 5 and 1 times 3, so a total of 8. Nitrogen needs more electrons to complete its shell, 3 compared to the 1 for hydrogen. So nitrogen will be a central element. Terrible arrow. That's used 2, 4, 6 electrons already, leaving us with 2. Duets complete for the hydrogens. So there's a lone pair on the nitrogen itself. And that's our final structure. Duets for each hydrogen and that octet for the nitrogen. Octet's complete. We've finished the Lewis structure. Let's see, finally silicon dioxide, which I can draw down below. Again, that electron count as we look at a periodic table. A bit messy here, of course. Silicon, element 14, so 1, 2, 3, 4 boxes to reach it. Oxygen, of course, 1, 2, 3, 4, 5, 6. So 4 electrons for silicon, 6 electrons for oxygen. That gives us a grand total of 16 electrons. Choosing the central element, silicon needs more electrons than an oxygen. Silicon needs 4 more, so we expect 4 chemical bonds. We'll connect it to the oxygens to give us our basic framework. Let's use 2 electrons each time, so we're down to 12. The remaining electrons fill the octets of the outer atoms. That's going to be the oxygens first. 6 for each of the 2 oxygens. And that actually exhausts our supply. But we're not finished because the silicon in the middle doesn't have an octet. It only sees 4 electrons. So we're invoking that last rule using electrons which are drawn as lone pairs, redrawing them as bonding pairs to the central atom. So a double bond there, giving us 2, 4, 6 electrons for the oxygen. Let's use another lone pair, turn it into a bonding pair. Why is that not? There you go. Thought it wasn't going to disappear there. And then that's a bonding pair now. Now as we look at the silicon, 2, 4, 6, 8 electrons. So 2 double bonds completes the octet, and we have a final Lewis structure again. That's the whole point of the Lewis structures, showing how the elements share electrons to complete octets and form stable molecules of matter. Let's take a look at some extra examples before we finish off. Did I miss a page there? No. Let's start by looking at nitrogen trifluoride. Again, following our 5 steps, count the valence electrons, 5 for nitrogen, 7 for each fluorine atom. That gives us a total of 26. Should be an even number because the orbitals and shells are filled with even numbers of electrons. We'll choose nitrogen as the central atom because it needs 3 electrons to complete its shell like neon, while fluorine only needs 1 each time. So with more electrons needed, we expect more chemical bonds from nitrogen. And we'll connect it to the fluorine atoms to give us our basic skeleton. That's used up 2, 4, 6 electrons to take us down to 20. We'll use those remaining 20 electrons to start filling octets. Always start on the outside and work your way in. Never add electrons to the central atom unless there's nowhere else for the electrons to go. So we've filled the octets of the fluorine atoms with 2 electrons to spare. So that pair of electrons goes on to the nitrogen as a lone pair. Octet is complete. You can see that with the fluorine and the nitrogen atoms. 8 electrons around each fluorine atom and 8 electrons around the nitrogen atom itself. 2, 4, 6, 8. We know we're finished when the octets are complete. Take a look at another. We might make this one our last one for tonight. Let me just take a peek. Yep, I definitely didn't do silicate today. So we'll leave that for Wednesday. So phosgene, which is the old mustard gas ingredient for World War I chemical bombs. We count valence electrons, 4 for carbon, 6 for oxygen, and 7 for each chlorine atom, but there's 2 of them. That gives us a total of 24. Looking for the element which is the most electron hungry, that would be carbon. It needs 4 electrons, while oxygen only needs 2 for an octet, and each chlorine only needs 1. So we expect more bonds with a carbon atom. We put it in the center and connect it to the others using 2 electrons each time. That takes us down to 18. We'll use the remaining electrons to complete octets, starting on the outside. And that's usually 6 electrons together with a bond to complete octets. But we run out of electrons before we can complete the shell of the carbon. You can see it there in the center, incomplete shell, as it can only see 2, 4, 6 electrons around it. These lone pair electrons have got nothing to do with the carbon. If they were, they'd be drawn as bonding pairs. 2, 4, 6. So incomplete octet. So we need to resort to a double bond to make that happen. Do we choose chlorine to supply us with the electrons, or do we choose oxygen? Well, obviously it's oxygen because you can see it down below. But why? And the reason for that is that just as we chose the central atom based on how many chemical bonds we expected it to make, we'll choose the supply of electrons for the double bond based on which of the remaining elements needs to make the most bonds. And that was 2 bonds for carbon compared to just 1 for chlorine. So each of the chlorines already has that 1 bond, but the lone pair turned into a bonding pair would give us the 2 bonds that we were expecting for carbon. So everybody has an octet. The carbon has an octet with 8 bonding electrons around it. The oxygen, double bonded, has an octet around it, 2 bonds and 2 lone pairs. And the 2 chlorine atoms have octets with 3 lone pairs and 1 chemical bond each time. Oh, excuse me. Oh, I hope you didn't hear that. So we are looking at covalency, the elements now sharing electrons to complete their octets and make them stable. And we can tell how many electrons the element needs by counting boxes from the element to reach the end of the table without counting that element's box itself, because we already have counted that box to get there. number of electrons needed, tell us the number of chemical bonds. We choose the most electron-hungry element for the central atom. We connect the central atom to the other atoms, start filling octets, and if we run out of electrons before we're finished, then start resorting to double and triple bonds, but only if we need it, only if we don't have an octet already. Okay, we'll call it a day there, and we'll pick things up with the 11 a.m. lecture on Desire to Learn, well, not Desire to Learn, on Zoom, I guess, on Zoom. Don't forget, office hours are now 9:30 at night, each night during the week. It's 8:27 just now. I think I'll get this up before office hours start. Good night. Stay safe. Wear that mask.